Okay, so today we'll go over just we'll begin ways to test whether series just converge or diverge. So like last time you had like geometric and telescoping, in which case I mean not only could you tell whether it converges or diverges, but you like if it converged you knew the exact number, right? Like geometric series is like a over 1 minus r, for example. So from this point on until I say near the end, um, you like you're either testing it diverges and like if it converges, you won't know what it converges to. Yeah. So okay, let's get started. So let me start by asking you all. hmm, Okay, so there's a theorem that says if a series sum an is convergent, then limit n goes to infinity an 0. So if you converge, like the thing that the sequence inside has to go to 0. Now, this theorem a priori is kind of useless, right? Because normally the question is asking you to check whether it converges or not, right? So it's kind of useless to like know if it converges and something happens. You normally you want to check if it converges or not. So but the contrapositive of this is useful. So the contrapositive. So this is test for divergence. So does anyone know what the contrapositive is? Like if P then Q, so this is the original, then what is the contrapositive and what is the converse? So converse is if Q then P. So what is the contrapositive if you had to guess? So anyone? So it turns out, if this is true, this is true. Yeah. So I mean, like these two are like the same thing in a way. So this thing is if not Q, then not P. So I mean, maybe an easy way to think is if it is raining, then I will use an umbrella. Is the same as if I will not use an umbrella, then it is not raining. Yeah. Hopefully that can convince you. So this thing is if limit, so think of this as your Q and this is your P, right? Then if limit n goes to infinity, so not Q is, so this is not 0, then sum an diverges. Yeah, so this is pretty strong. So this is something I would go to if it asks you whether a series converges or diverges or not, because you're done, right? If the limit's not 0, you're done. Like you're flat out done with the question. Just write diverge, test for divergence, move on to the next question. So it's pretty strong. Yeah. So but I'm telling you the converse is not true, right? So the converse is if limit n goes to infinity, an is 0, then sum an converges. Yeah, this is not true. Yeah. The classic example is sum 1 over n. So you can check that this is my an, right? So this thing is 0, but this thing diverges. In fact, this is called the harmonic series. So let's sort of see why, right? I mean, the book does it, but if you write out the terms, I'm just going to go to 8, and then hopefully you see the pattern. So this is certainly bigger than if I replace the 1/3 with 1/4, right? Because obviously 1/3 is bigger than 1/4. So if I replace it, it's going to be smaller. And if I replace all these with 1/8, and if you just keep doing this, you're going to see you get a half. This is a half. This is a half. So this is bigger than 1 plus, and then you have like an infinite sum of a halves, right? I don't know, I equals 1 of like 1/2. Yeah, that's the idea. And what's infinite sum of a half? Can anyone tell me what that is? Sorry, there should be like equal. So what happens if you add a half infinitely many times? What do you get? Exactly. So you get that this is infinite. So this thing is bigger than infinity. So what must it be? It has to be infinite, right? So this thing has to diverge. Yeah. So yeah. So keep in mind the harmonic series is a good example to have. Okay. So with that in mind, let's go over the second test. And this is related to why we learn integrals, I guess. It's called integral test. So the idea is basically, before I write it, it's like, whatever integral, whatever happens to integral, happens to sum. That's the way to think of it. Uh, it's a bit not correct in a way if you think of it. But I'll just explain the little quirks. So suppose f is continuous, positive, and decreasing. So let me just say the decreasing part isn't that bad. Yeah. Function from 1 to infinity, and an is f of n. So an being f of n just means you replace the x with n. Yeah. So like if f of x was like sine x, then an is sine of n. Obviously, this function will not satisfy the criteria because it's not positive from 1 to infinity. But that's what we mean by an is f of n. And then the integral says basically I, if integral 1 to infinity f of x dx converges, then this converges. So if you could solve the integral and whatever happens to that in terms of convergence or divergence, it will happen to the sum. diverges. So this is good for sums you see that you can integrate. Then sum n equals 1 to infinity. Okay, let me ask a question. So why is, so if we assume we are positive, why is decreasing not that big of a deal, I guess? So so like if you are positive and let's say you're not decreasing, chances are you're not going to zero. Do you agree with that? I mean, you could go up, down to zero, but like chances, but those functions are pretty hard to write. So like, I mean, chances are if you're positive and you're not decreasing, you're not going to go to zero. Do you agree with that? Or at least not agree, but like kind of agree most of the time. That's true. So if you're positive, then like chances are if you're not decreasing, you're not going to zero. And if you're not going to zero, well, the test for divergence makes you finished. You're pretty much done. Yeah. So the decreasing part is really, not a big deal, You still have to check it, but if it's not decreasing and it's positive, you just use test for divergence most of the time. So let me just tell two things. The one is starting point, right, of the sum. Yeah. So for example, like if you wanted to show sum n equals 3 to infinity, if want to show converges slash diverges, right? Then you would do integral 3 to infinity. Yeah. So this one is like this one. Yeah. So that's another key point. And obviously, you would need continuous from 3 to infinity. Yeah. Everyone get that? So, and the second part is if the converge part is just converge. Yeah. Do not assume anything about number. So basically I'm saying like suppose integral 1 to infinity f of x dx. Let's say it's 5, yeah? So this converges, yeah? Agree? I mean, it's a number. So by this test, we get sum n equals 1 to infinity a n converges. It does not mean this, okay? Do not ever write this. It does not mean that this is 5 as well. Yeah. You do not know the value of this. Yeah. All you get that is if this thing converges, this thing does also. Yeah. You don't know like what it doesn't need to be equal to the value of the integral. Yeah. So that's this, I guess, yeah, that's the most important thing, I guess, because a lot of people think if the integral is 5, the sum is 5. That's not true. Okay, and then the third thing is technically you just need decreasing after a certain point. After a certain point. Yeah. Like the first few terms don't matter. I'll sort of show you what I mean. It's a bit pedantic, but I think it's good. So let me just explain that. So how to like deal with, something that doesn't do that. In Q plus 1. Okay, so let's consider f of x let's use integral test. Yeah. So How would I check it's decreasing? So in Math 2A, how well how can you relate this to Math 2A? How do you check something's decreasing? Find derivative, and what does the derivative need to be for it to be decreasing? Good. Let's do that. I'm just gonna go really quick. So this is 2x x squared plus, or sorry, x cubed plus 1 minus 3x to the fourth. Yeah, everyone good? So, because derivative of x cubed plus 1 is 3x squared and then times x squared. Yeah. Okay. So this is what? This is negative x to the fourth plus 1. I was hoping for a better example, but oh no, plus 2x. Yeah, plus 2x. Sorry. Okay. And then over square. So this thing's always positive, right? So we don't have to care about that. Now, for x equal to 1, right? It's still positive, right? Do you agree? Like negative 1 to the fourth plus 2. That this is 1. It's still positive, but once you're like bigger than or equal to 2, you sort of see that it's decreasing, right? I mean, because x to the fourth grows way faster than 2x, right? So do you see that this is less than 0 for like x bigger than or equal to 2? Do you all see that? Yes? No? I.e., if the derivative is negative for x less than greater than or equal to 2, then that means it's decreasing when x is bigger than or equal to 2. Uh, well, it's derivative of this, right? Times x squared, right? So you should get that, right? Agree? Am I going crazy here? Yeah, that's the quotient rule, right? Oh, okay, cool. Yeah. So do you all see at least do you all agree that when x is bigger than or equal to 2, your function is decreasing, but at 1 you are, in fact, you're increasing because derivative's positive. So if you're to be like, let me just say pedantic, to use the theorem, you need the function to be decreasing, right? But you check that it starts decreasing at 2. So what you do is, yeah, you do that. And then you say, okay, well, this is just, if I plug in 1, I get a half plus sum n equals 2 to infinity, n squared over n cubed plus 1. Now you're going, right, this is the term n equals 1, by the way. Right, you can split it up and then you apply the test here. Yeah. So that's what I'm saying by it decreases after some point, because you can always do this. Yeah. And like, and after some point, like the terms before is a finite number, right? If I add finitely many numbers, like it shouldn't affect convergence or divergence, right? It's only when you add the infinite part. The infinite part. Yeah. So yeah, so if you want to be pedantic, you apply this here, and then you do, integral 2 to infinity x squared over x cubed plus 1 dx. So I'm just gonna be quick about this. So this is limit t goes to infinity of t, and we're gonna do a u sub. So u is x cubed plus 1, du is 3x squared dx. So at this point, you should know how to do this. So uh, x squared over, oh, sorry, let me not put the bounds yet. And dx is du over 3x squared. 1/3 integral. So when t, this is t cubed plus 1. This is 9. Yeah. And then you have 1 over u du. So this is limit t goes to infinity. This is natural log, right? And let me just write that this is, 1/3 and then natural log of u, and then you evaluate at the bounds. So this is 1/3 natural log of t cubed plus 1, right? And then minus 1/3 natural log of 9. So when t goes to infinity, where does this term go? I mean, I don't care about this because this is a finite number, but like, where does this go when t goes to infinity? What's natural log of like infinity in a way? So where does natural log go when you head off to infinity? Let me draw it for you. Yeah, it's infinity, right? So this thing's infinite, so this thing diverges. And I mean, if this goes off to infinity, I mean, if this diverges, this thing will diverge. Yeah. I mean, a finite number isn't going to change anything. So this thing diverge. Good. So let's maybe make use of your. Let me just ask a new question then. What about this? Oh, by the way, before this, let me just tell you a quick way, at least for like your final, to like get the answer without doing stuff. When you have like rational functions, you want to look at how it behaves like. So for example, do you all agree when n is large, this one does not matter? Yeah? Do you all agree with that? Like when and like we only care about when n is really large, right? Starts getting really large. So when n starts getting really large, do you all agree that plus one like means nothing? Like for example, like 1 million, like over 1 billion plus one is kind of the same as like 1 million over 1 billion. Yeah. Do you all sort of agree with that? If you like. So this thing behaves like what? If I just exclude the one, this thing behaves like sum n equals 1 to infinity n squared over n cubed. And what is n squared over n cubed? This thing behaves like 1 over n. and you all know this diverges. So that so like you should expect this to diverge. Yeah. So that's like a way to just eyeball it, I guess. I mean, the proof is integral tests, but like, you know, just eyeballing it, you want to use this. Yeah. Uh, okay. Now, what about this? So I gave you integral test, and what was the first thing I went over before integral test? So we learned test for divergence, right? So that would be the go-to thing. I mean, I didn't use it here because test for divergence doesn't work because this thing actually goes 0 to 0. But here you check it does it, right? This thing does not exist, right? I mean, this sequence keeps alternating, right? There's no way this thing can converge to something if you just keep alternating between two different numbers, right? I mean, two of the same different numbers. How about that? So, I mean, since it says it doesn't exist, right? We just check if it doesn't exist, it's not 0, right? For sure. If your limit doesn't exist, your limit cannot be equal to 0 because if you're equal to 0, that would mean the limit exists first of all. So, so this means this diverges by test for divergence. Yeah. So let's just be clear. Like when I write the limit is not 0, I guess implicitly I'm saying it also includes or limit does not exist, right? So does not equal to 0 means some people might interpret it as like it's 5 or something or 6. So but what I mean is like as long as it's not 0, you're done, and that includes like your limit not existing. Okay, let's do something fun. It's from your previous homework. It's related to your previous homework. What about this? So do you all agree it's decreasing because in this case it's easy to check this decreasing because f of x is 1 over x ln x. Both of these things, both of these functions are increasing. So when you do 1 over it, it's going to be decreasing. Yeah. So, okay, and it's certainly positive, right? So we could use like integral tests. Yeah. All this stuff hold. Now I claim we are done. Do you all recognize this? Does anyone recognize this? You did this before on your homework. In fact, on your homework, I mean, the two doesn't matter, but on the homework, you check something else. There was a P there, right, on your homework. What was the result? Do all of you remember? This converged for P what? What was the condition? You all had this on homework, by the way. Anybody? In fact, it was your most previous homework. Yeah, it was your most previous homework. Because that was the one I remember grading, like the day after you all submitted it. So what was the condition? I'm sure one of you must have gotten it correct, right? On the homework? I'm pretty sure I gave people full credit on that. Or like most people full credit on that. Yeah. I mean in this case P is 3, right? So let's just say from homework. I don't want to do it again. So from homework you get that, this thing converges. So this thing converges. Yeah, and you're done. Let's do like 2 more, I guess, just so we all see what's going on. I mean, we could do like 1, I guess. 1 to infinity arctan of n over 1 plus n squared. So again, I mean, you could check the limit as it goes to infinity. This will go to 0. So test for divergence doesn't work, right? Because you'll get like pi over 2 over infinity. So from here, you wanna consider this function. And now you say the same thing, right? Check it's decreasing. So let's check the derivative. In this case, it's nice on this side. This is 2. The derivative of arctan is 1 over 1 plus x squared, and then you're multiplying by 1 plus x squared. So these cancel. And then derivative of 1 plus x squared is 2x, right? Yeah, it should be 2x. And tan inverse of x, right? So you get 1 minus 2x tan inverse of x over, yeah. So these are increasing, right? Tan inverse and x. So you just need, so if you're already negative at, so these will only get bigger and bigger. So if you subtract a bigger and bigger number, so if the first term is negative, all the next terms are negative. So you just check it, right? When x is 1, tan inverse of x is like pi over 2. The pi over 4, sorry. My bad. Pi over 4. So this thing, right? So 2 times 1 times pi over 4, right? Because x is 1. This thing's pi over 2. And like pi is like 3.14 something, right? So 3.14 something divided by 2 is certainly bigger than 1. And I'm doing 1 minus something bigger than 1. So this is always negative, right? So from here you get it's decreasing. It's certainly positive. Arctan is always positive, as long as you're above 0. The bottom, you're squaring, of course, so you're always positive. You're adding 2 squares. So from here, you just integrate, right? Arctan of x over 1 plus x squared. And here I'm trusting you all know what to do, right? So like let u sorry, arctan of x. Then du is 1 over 1 plus x squared dx. So you get limit t goes to infinity, integral arctan of t. And then arctan of 1 is pi over 4. And then you just get u du, right? So this is, obviously, this thing goes to squared evaluate at 2. And you're evaluating at the bounds. So this thing becomes, right, tan inverse of t squared over 2 minus pi over 4 squared over 2. Yeah. And I mean, this is a finite number. I mean, this part. This part's a finite number. So we only really care about the first one. Where does arctan go when t goes to infinity? Pi over 2. In other words, it's a finite number, right? And when I subtract two finite numbers, this thing converges. So this thing converges. Like I don't even care what the number is. I just care it converges. And then so the sum converges by integral test. Let's do one more and then we will call it a day. So sum. Let's do this. How would you do this? So again, rule of thumb, always use test for divergence first. So do the terms inside go to 0? So what do you get when you take the limit of the terms inside? And you're done, right? So you're done. So for those of you who don't know, who forgot, right? I mean, how you would explicitly do this is you would factor out the n squared. This is really bad writing. So this, you factor out the n squared, right? These cancel. So this becomes 1, this becomes 1. And then when n goes to infinity, this thing goes to 0, right? So this thing goes to 1/3, which is not 0. So this thing diverges by test for divergence, right? Is everyone clear on like these two tests and how to use them? You'll learn a lot more, but these are like the two starter ones, I guess. Okay. In that case, I could just leave 10 minutes for like homework questions or whatever. And if you don't have it, you can go. Yeah, I think, and also by the way, I think it's a holiday Monday. So yeah, I'll leave the 9 minutes for like as office hours. If any of you have questions.